society, technology, and science. Before I introduce our speaker, Andrew Belmonte, I'd like to say a few words about Gil Coe. Gil joined the NCSU Mathematics Department in 1964, and during his 40-year career at NC State, he authored over 70 research papers, published a book, and served as mentor of 11 PhD students. Gil's lifelong commitment to education was a cardinal feature of his tenure at State, and he taught and influenced thousands of students over the course of his career. After his retirement in 2004, he continued to teach part-time and actively participate in the research and educational activities of the department until his passing in 2009. His generous spirit, powerful intellect, and profound integrity remain an inspiration to his friends, family, and colleagues. The Coe Lecture wouldn't exist without the contributions of numerous faculty, former students, our staff, and just general lovers of math and the sciences. I especially like to thank the Coe family who are here today, some of them, for their generous donations, which helped start the endowment that funds this lecture series. If you are a lover of math outreach, I encourage you to talk to me or Brock Matthews, who is here, about the possibility of making a contribution to help us improve our outreach activities. There's also more information about that on the back of the program if you're interested. Today's co-lecturer is Andrew Belmonte, Professor of Mathematics and Material Science at Penn State University. Professor Belmonte received his PhD in physics from Princeton in 1994. After postdocs in France and the University of Pittsburgh, he settled at Penn State in 1998. Professor Belmonte has received a number of distinguished awards, including a Sloan Foundation Fellowship, an NSF CAREER Award, and a number of visiting research positions, including at the NIH, the University of Paris, and Harvard. Professor Belmonte is well known for his work at the intersection of mathematics and aspects of the world to which it can be applied. He's also well known, and we're going to see shortly, for his engaging lectures. Today, we'll hear about applications of mathematics to games, decisions, evolution, and chance. Please join me in welcoming Professor Andrew Belmonte.
Thank you. Can you hear me okay? Can you hear me? Good, thank you very much. I really would like to thank Seth, Michael Shearer, and the entire math department here at NC State, and for inviting me and giving me the chance to talk with you today, and also giving me the honor of giving the 2018 Kwangil Coe lecture. So thank you very much for that. All right, it's time to start trying the equipment you've given me. Thank you. What's a game? It's a situation, maybe with rules, this game, and you play. Usually against someone else. You move your queen, you roll the dice, place your bets. Now, I'm not talking about sports games, and Seth just mentioned I come from Penn State, so you might expect that I'm going to mention football at some point. I'm not going to mention football. On the other hand, I am speaking in North Carolina, and you might expect I'm going to mention basketball. It's a game. I'm not going to mention basketball either. So if you're here to find out about NCAA rankings or predictions for next year's bracket, I'm sorry. I'm not going to mention that. However, what I am going to talk about is this kind of game, in my Cézanne, two players facing each other, literally, and engaged in a decision-making process in which they are trying to win. They're looking at their cards. They are not sure what they're doing, right? What do you do in that situation? How do you decide? What do we do? As humans, what do we do when we play games? Well, actually, I want to continue by talking about something a little bit different. Humans playing games against machines. You may have heard about AlphaGo. Right? So recently, 2016, Google's DeepMind computer program, an AI realization, became the first program to be a human professional Go master. And this was considered to be a great breakthrough in computer program, playing a human being in a game. That says something about what we might be doing when we're playing a game, because computer, well, I guess can beat us. I have a chessboard here, and you probably remember, I certainly remember this when I was younger, 1996, the chess grandmaster Garry Kasparov lost to IBM's Deep Blue. At that time, it was quite big news. He was subsequently unable to beat it again after that. So some sort of breakthrough at that time led the computer to be able to best us playing chess, this game. I don't know, I'm sort of forced to conclude that chess is easier than Go. Because it's, what is that, 10, 20 years, something like that, between the two. But it's difficult to say what's needed for either one of these. So how long have we been playing games like this against each other? This is an image taken from an Egyptian archaeological finding showing the game Senet. And this game, as I understand, goes back to at least 3000 BC, so that's 5,000 years plus. We're playing games against each other. And they could be board games, Go, Shangxi, Chinese chess, or card games, bridge, poker, canasta I have to mention, since I remember my family playing canasta. Texas Hold'em is a game I enjoy playing. I'm not very good at it. I'm not going to tell you how to play any of these games today. Parcheesi. Why is there no Deep Blue or AlphaGo program to try to best our Parcheesi players? Or what about Monopoly, or what about Apples for Apples? What about this game? It's Nate DeGraff. What is this game? Where are you, Nate? Oh, there you are. I don't know what this game is. Actually, this is from the poster, and I really love this image. I don't know if this is a real game or it's just some sort of paste together of, but I mean, this is great. Look at this. We've got, clearly there are rules involved. I mean, there's squares that at least go up to 37. I don't understand why the pieces are geese, but I appreciate the biological reference there. I like that. And then right here, front and center, dice. So, is this a real game, Nate? You don't know? All right. So the dice, I liked the dice in that image because, indeed, some of these games I've mentioned involve randomness, and that's interesting, right? Because like rolling the dice in Parcheesi certainly, or even in the cards you're dealt, right? You don't get to choose the cards you're dealt; they're shuffled, they're given to you, right? Or even games where you're drawing cards, like 21, you're drawing cards from a deck. There's randomness. So I've been talking about strategy because, you know what, you want to come up here afterwards. I'm not very good at chess either, but if you want to, give me your best opening, there's my first move. There's no randomness in that. That's what I always do. I always push the queen's pawn up 2 spaces. But so chess and Go, there isn't really this intrinsic randomness unless you just start playing randomly. But so I want to talk about today, does randomness interfere with strategic decision making? It sort of seems like it would be noise. Why would we include randomness in a game? Right? On the other hand, I know for a fact that randomness in a game is a popular thing among humans, right? There's an entire industry devoted to randomness in games. Las Vegas, Monte Carlo. In fact, I was once in the casino in Monte Carlo, and I got to witness some roulette. I also don't like gambling. I like giving away my money on some sort of random process. But at the roulette table, they have a list of all the previous numbers that have hit, listed. And it's very Monte Carlo, very fancy. I don't think I was wearing a tuxedo, but there were a lot of people wearing tuxedos. This was not a James Bond scene. This was actually people losing significant amounts of money. And when you saw 4 or 5 red numbers in a row, people would say to each other, "It's running red. The table's running red." People would crowd around and they'd start putting money on red. But let me remind you, it's a ball that spins around this rotating disc and lands in one of the squares. It's not running red, right? But it was excitement. People putting money, oh, it ran red again. Oh my God, I just won. I just doubled my money, right? Then they'd say, I think it's falling off now. You see a blue black. There's an entire imaginary world of what this table was doing. Enjoyment. Why do we enjoy that? Why do we like? I don't, but as humans, why do we like that? Some question going on. So I want to talk about these two very different types of games. Beating the odds, playing against the table, beating Monte Carlo, beating Las Vegas, beating the grandmaster, playing against some chess genius and winning. What do we do when we try to play a game of strategy? What do we do when we try to play a game of chance? And why do we enjoy those things? So I want to explore this today, and I want to talk about the mathematics that's developed around it, okay, to try to describe each of these two games. And I'm going to start with probability and randomness. So let's do that. Randomness. What are the odds? Right? So I've taught probability a few times. I've never taught a full course in probability, but I often have to teach probability in game theory and other courses that I teach. And it's always a question to me, how do you first introduce randomness? What is it? What is random? Right? What does it mean to be random? Well, unfortunately, I have a physics background, as you just heard. I'm a math professor for 20 years, as you just heard. I've sequestered myself in tiny offices in ivory towers. And so, how do you explain probability? I have no idea. I don't, I've been living in this monastery. So I've asked a lot of people, what do you consider random? What do you consider random? So one of the interesting questions that I got is something that I know very well. You're speeding along. Here's my pointer. You pass a police car, right? You stop. I would call it a speed trap. It's the law. You're supposed to not be speeding. Police car sitting right there. He goes zooming by. Usually I'm changing the radio or doing whatever, talking to someone, and I'm watching them in my rearview mirror. Do they come and pull you over or not? So somebody told me randomness. It's random. Sometimes they do, sometimes they don't. They definitely don't always. Now, in the police car, if we were to zoom in here, there's something going. Maybe they're not paying attention at that particular moment. Maybe they just decided that's not enough. I'm looking for someone who's doing over 30 miles over, not 25, 20. I don't know what they're deciding, right? But from the point of view of randomness, I do it, and sometimes I get pulled over. I do it, and sometimes I don't get pulled over. It seems random. I'm doing exactly the same thing. I'm doing 85. Or whatever I'm doing. Is that too fast? How fast do you drive? And sometimes I get a speeding ticket. I hate that feeling. Sometimes I get away free. I guess it's like gambling. But maybe I do like to gamble. All right, so let's talk about how do we define mathematically what's going on. So I need to tell you what a probability is. What are the odds? How do we describe a random event mathematically? So the field of probability that's been developed over the years has an answer to that. The probability is a number u between 0 and 1, and it's got two ends that are certainties. If u is equal to 0, the probability is 0. That means it cannot happen. Like they never pull you over. And they cannot. There's no question. Or 1, they always pull you over. Something that's already happened. In between is uncertainty. It's a number between 0 and 1 that tells you that it's random and how random is it. Okay, oh, now we're doing better. How random is it? Not just it's random. What's the probability? Right, so as an example, is it going to rain? Let's say you say there's a 30% chance of rain. That would be u is equal to 0.3. This is sort of, okay, sometimes it lines up fine. Should I move this? It lines up fine. Throat. It's sort of random. 30% chance of rain. You're looking at the sky, and suddenly you see a cloudburst, or you see it somewhere distant, and you want to know is it going to rain on me or you. 30% chance is what they say on the weather. Or, I guess for you, it would be a 1% chance of snow. When I left Pennsylvania yesterday, it was snowing. Lightly. It's still snowing in England. Okay, so I don't know what the chance would be of snowing here in North Carolina, but this would mean, not very likely. It's close to impossible. We could definitely say that. Whereas if this was 0.95, it would be close to certain. Right? Well, what does that really mean? Okay, so I have to tell you what this number u really means. It's best defined, or one way to define it, is in terms of the limit of events. So let's say the event I is raining. Okay? When I teach probability, I love to talk about this because when you say there's a 30% chance of rain, what you really mean is if you had 12 identical days, that 30% of them you'd have rain, 70% of them it wouldn't be raining. That's exactly what it means, mathematically. But actually it's not just 12. We need to take the limit. So whatever the event is, here it's raining, we need to take the limit as the number of rectangles of identical days in North Carolina goes to infinity, and out of those identical days, only a certain number of them have rain. And that ratio in that limit approaches the probability that that thing is going to happen. That is mathematically well defined. It happens with probability u, or it doesn't happen with probability 1 minus u. This requires that it's a random event, that it's independent each time, and that it has this property that it either happens or it doesn't happen. Either it's raining or it's not raining. We're going to say that. That's called the Bernoulli trial. Okay, coming from Jacob Bernoulli. Okay, so flipping a coin, rolling a dice, 3. Okay, so what's the probability that I get a 3 when I roll the dice? Well, I have to think about all the times I roll the dice, and then how many of the times do I get a 3? Or I can have some sort of theoretical insight, and I can calculate, well, how many sides does your dice have? And they're all equally probable. That's a little harder for the rain case, but I assume that's what they're doing at Equilibrium. I have to go, I can't resist, since I mentioned Bernoulli, I have to just give a little snapshot of history. And the history of the development of probability is fascinating. A lot of theoretical and philosophical discussions. It took us a long time to get to this point where we can say 30% chance of rain and we know what that means. Okay? It took us, going back to the 1600s here, Christian Huygens, painting of him there, 1657, one of his major works. Jacob Bernoulli, 1713, it's actually much earlier. This is a page from that, it was published after he died, and one of the early issues that they argued was about expectation or expected value. I'll come back to that in a moment. I also just can't resist telling you, Bernoulli is also the person who first discovered the number E. I mean 2.71828, that E. So if that comes with another context. He was the first person. He was doing the limits of compound interest. Okay, so that's another whole talk. How much mathematics has come to us from business, from insurance, right, from mortality tables. So I just thought I'd mention that to you. So this is very brief. This is just one slide on history. Two names: Kwangil, Bernoulli. Okay. So I want to talk about a Bernoulli test, the way Bernoulli talked about it. And the way he talked about it in that book I just showed you is about pebbles. Excuse me. Pebbles in an urn. So he said urn. When I hear the word urn, I think of a Grecian urn. So that's why I'm showing you a picture of a Grecian urn. I don't think he used a Grecian urn. And I don't have a Grecian urn. What I have is a hat. And ping pong balls. Okay, so what I'm going to do is I'm going to put 3, 6, 9 white balls, orange ping pong balls. I'll put one of these in there. Okay, so the Bernoulli trial, or the way Bernoulli formulated it in terms of this urn, is that you have a number of balls in an urn. Here they're in a bag. And I don't know which one's which. I stick my hand in. What's the probability I pull out an orange one?
1 out of 10.
1 out of 10. Right? Wow. Good. What's the probability that I pull out a white one? 9 out of 10. But I've only done it once. So, what's going on, right? So I can take this. So now there's replacement or without replacement, right? So in probability, you have to talk about what do I do next? I put it back. And it's the same. Where do I? And it's Seth. Seth. Now what's the probability that I pull out an orange?
1 out of 9.
1 out of 9, right? Because we somehow know it's equally probable because you think I'm actually shaking it really well, and I'm not. This is not a magic talk. Is no. You know, I'm not going to pull out a bird or show you that they're all orange or something like that. There's actually still, there's one orange one in there, and there's 8 white ones in there. Okay, nothing funny going on. I'm just not looking. Except I sort of know where the orange one is, but now I'm mixing it. Okay, so this is the way, I mean, it's the way we teach it. When we teach probability, we teach it in terms of that. But it's also the way in which Bernoulli first thought about it and was sort of a clarifying experiment. Right? How many times do I have to reach into the urn before I get the orange ball, yellow ball? I guess I forgot what color they were. This is an example of a question without an answer. And I sort of love this part of the story. Okay, before we understood the mathematics of probability, there were these puzzles. And one of the puzzles was people would say, how many times do I have to flip a coin before I'm guaranteed to get heads? Guaranteed. Okay, I think there's a lot of you already know that there is no amount of time that you can flip a coin that you're guaranteed to get heads. In fact, there's an entire play by Tom Stoppard based on this coin that always comes up. Is it tails or heads? Rosencrantz and Guildenstern are dead. I don't remember now, but throughout the play, someone's flipping a coin, and it's always coming up heads. Let's say. That's possible. Okay, so at the time, how many times do I have to reach into the urn before I get one yellow ball? This would be with replacement, by the way. So this is not now I need the ball back, Seth. All right, so with replacement, how many times do I have to do it? Well, each time I do it, each time I do it, it's the same as the previous time. So it gets smaller and smaller. The probabilities change with time, but they never go to 0, they never go to 1. There's always a small chance that I just never, ever, ever pull out the orange ball. Right? But early on, there's a lot of time spent on this question before it was realized that this question actually doesn't have an answer. It's part of the theory is to understand that you can't ask this question. It's the same for dice. How many times do I have to throw the dice before I roll a 6? How many times do I have to throw this thing before I get a 6? Right? I can't ask that question. Instead, we have a different kind of answer. Mathematics, the mathematics that was developed for probability, brings us a different kind of answer. And the answer is in terms of what's called the expected value. What number do I expect to roll? Well, so its expected value is what it's called. It's sort of more of an average value. What number do I expect to roll when I roll the dice? Well, as you just did for the balls, it's probability 1/6 of getting a 1, probability 1/6 of getting a 2, etc. So the expectation of what number I'm going to get when I roll it is just sort of this weighted average of the 6 different numbers, each multiplied by the probability of getting each one. Sum it up. Right? Now, as a mathematician, I like to write it like this. Sum probabilities, well, they're all equal, so there's 1/6. And these are the different values for the ith face on the dice. Anyone know what it is? I'm hearing 3 halves? 3.5? Oh! Ha! 3.5. Correct. I fract out the 6, add them up, 21/6, 3.5. That's right. I would like to point out that you can never roll a 3.5. Right? It's just like the situation, you've probably thought about this, comparing the average grade in the class. You might have noticed that it's possible that nobody in the class actually got the average grade. Right? So similarly, we call it the expected value, but in fact you cannot roll it in any one given realization. Or the average height. Same thing, there may be no one who actually has the average height. Okay? So actually there is a game based on Bernoulli trials of sorts without replacement. I don't know if you have a, I'm very, as I said, I don't like gambling. I definitely do not like buying lottery tickets, but Powerball or other things like this, right? I've heard all sorts of strategies. I can take one of these balls, or I can write 37 on it. We can fill them all in, throw them in here, shake it up, and then I pull out 5 of them in order or something like that. It gives me 5 integers in order. And whichever one of you picked that wins, what is it, 400? Is there a Powerball here in this state? What is it? It changes, right? But when it gets big, suddenly everybody's talking about it. I don't follow it, but I know when it gets big because suddenly certain people I know are saying, 400 million. I'm going to buy it, and then there's all these strategies. How do you pick your numbers? Or I always pick, I use the fortune cookie that I got from my dinner at the Chinese place. Or I pick, I don't know, the last phone number. I don't know. Okay? It's like the table running red. Right? It's a chance thing. It's ping pong balls that are being mixed up in some machine and you're pulling them out. 32, 16, 19. What strategy are you going to use to choose those numbers? All right, I would like to go back to talking about actual games of strategy. So, let's talk about not probability, but game theory. So at the beginning I said, we have these games we like to play. We like to play roulette, apparently. We like to play with the slot machine. Go to Las Vegas. I've heard they have them in the elevators. With Las Vegas? That's what I've heard. I've never been to Las Vegas. Slot machines in the elevators. You can't wait to get down there. You can't get down there fast enough. They're in the elevator. I wish there was an espresso machine in my elevator. That's what I can't wait to get. Right? But there's also this other kind of game, which is strategy games. Okay, so now I'm back to cards. And I want to talk about this other area of mathematics, game theory. So now let's switch. What's game theory? So the kind of game that game theory refers to is how do you decide what to do? Now, I'm going to focus on this gentleman right here, this young man. Please notice that this is not legal. And I don't know if this is whist or what. Whatever game this is, I'm pretty sure this is not legal. There's some sort of table talk going on over here. She's pretending to pour the wine, and this guy has no idea what's going on. I saw a poster with a bunch of people playing cards, and it said, if after 20 minutes you don't know who the sucker is in the room, then you're the sucker. So he has no idea what's going on. But the fundamental phenomenon that game theory tries to treat is you're trying to make a decision, and there's uncertainty. You're trying to make a decision, and there's uncertainty. But the uncertainty is not about the weather or the roll of the dice. The uncertainty is about these other people you're playing against. They're trying to do exactly what you're trying to do. They're trying to make decisions, you're trying to make decisions. I moved, now it's your move. Or we move at the same time. We all put our cards down at the same time. Whatever the rules of the game are, I'm trying to think against someone else who's trying to think. That's game theory. Okay, so I think I just said all this. Using all the information available, the player decides what action to take. That's a choice of strategy. And then you win or you lose. We're talking about competition. We sometimes think about cooperation when we talk about game theory, but that needs to be included. That would be yet another talk that I can give. Benefit or loss. There's always some payoff. And of course, the real question is now, how do we represent this mathematically? We talked a little bit about Bernoulli. We talked very little bit about probability. What do you do for this? Now, in the case of game theory, I have to admit to you that I have ulterior motives for thinking about it because I'm interested in biological systems, and I'm interested in cancer, modeling that. And game theory is a little bit closer, in my mind, to modeling biology than some of the other things we've talked about, or some of the other mathematics that I teach in the calculus class, or my differential equations class, or my prime numbers, whatever I'm teaching, this is the one I like. Because it's about playing against someone who's playing against you. These cells are trying to grow. There may be an immune system that's saying they're okay, or there may be an immune system that says, these are invaders, we need to remove them. It sort of seems like a game, or there could be, there could be a mouse trying to get across the floor, and there could be a cat chasing that mouse, right? It seems like that kind of mathematics, the mathematics that describes the game, seems a little bit closer to biological things, at least in my mind, and in other people's minds as well. Okay, so I just want to mention that. All right, so here's your one slide on history of game theory, and this time without pictures. I want to mention a few names here. Really, the founders are Borel and von Neumann. Okay, Borel, you can argue if you read his 1921 paper, he's thinking about methods of play. He wrote a matrix, okay, but he didn't seem to fully talk about it. Like John von Neumann, really, this is when it started, 1928. Very much the modern theory of games. And then, right after World War II, von Neumann Morgenstern, it's a very important book. And then, of course, John Nash famously advanced the field quite a bit. Cournot, this is earlier. You can go back and sort of find early roots to it as you go backwards, but the word optimal appears here. Right? Cournot was thinking about businesses competing against each other. What's the optimal way for them to do so? One of the things I'm going to tell you about game theory is it has the ability to be non-optimal. I think that's a nice feature. If you look around the world, economics, politics, or you look around biology, there's lots of non-optimality going on. So another reason I think this could be a good model for such things. Okay, so I'm going to talk a little bit about dilemmas as well, because when I show you a payoff matrix and we start talking about choices, it's possible that the best choices, or the ones that are chosen, are not the optimal ones. In other words, the best thing for you to do, given the fact that you're playing against someone else who's trying to do the best thing, may lead the two of you to something that's really not a good situation. Okay? So, and the game I'm going to use for this, there's a lot of examples, but the one I'm going to use is what's called Prisoner's Dilemma. I don't know if you've heard of that game before. I think it's probably the most well-known game in game theory. I'm going to show you the other one too, rock, paper, scissors. It was posed in the 50s in the Rand Corporation. If the number 1950 means anything to you, it should mean Cold War. Two large countries with an enormous number of nuclear weapons ready to launch them at each other. And Tucker had the version that includes two prisoners, and I want to talk about that right now. So, prisoner's dilemma. Okay, so Seth and I commit a crime together, and we were arrested for that crime. And they separate us, and they try to make a deal with each of us. They have some evidence that we committed the crime, but really not enough, and they suspect that there's more evidence to be had. So they make each of us the offer that if you give me full evidence on, well, in my case on Seth, in Seth's case on me, cut a deal, we'll give you less time. Of course, the person who doesn't cut a deal gets really hammered. So now you've got full evidence against the other guy. All, whatever. Where's the gold buried or whatever we did? Where's the painting we stole? But of course, it's possible that both of us cut a deal at the same time. Well, then they promised that they would cut us a deal, but that whatever they'll say, if both defect. So it's called cooperate and defect. I would like to point out that cooperate here does not mean cooperate with the police. It means that cooperate, Seth and I cooperate. Let's not squeal or whatever you want to call it. Defect means I'm just doing what's good for me. Seth's on his own. Okay? Or you might say the same thing. If we both say that, defect, then, okay, so the example I'm giving is, without a deal, we're only going to get 1 year in jail. That's cooperating. If the person who turns in and cuts the deal by themselves gets a half year, the other guy gets 10. But if both defect, then they can't really send you away for 10 because they offered the deal, so it's 3. The dilemma comes from the fact that, as I'm about to show you, you should always defect. You should not cooperate, according to game theory. But that leads, if we both defect, we each get 3 years. If only we had both cooperated, we'd only have 1 year. What is it that leads us to do that? Right, so now it's time to show you the payoff matrix. So this is not your regular garden variety, off the street payoff matrix, I should say. This is a payoff matrix. It's not exactly the same as just a regular matrix, because you see each entry has 2 numbers with a comma separated by a comma. So let me explain that. There's one player who's the row player, choosing between cooperate or defect. And that's represented by the first C, or D, first letter. This is cooperate for player 1. So player 1 is the row player. Let's say player 2 is the column player. It doesn't matter which number we are. And so all the numbers I just mentioned are here. I guess they're actually slightly different. Was it 10? Oh no, I updated one and I didn't update the other. Sorry about that. Okay, so the numbers are a little bit shifted here. It's not a half year, it's not 10 years, it's 8 and 1. So if player 1 and 2 both choose cooperate, that's cooperate, they each get 3 years. I've also switched something else. Now I have to tell you something else. Let me back up. Now we know why the numbers are. Excuse me for that. In game theory, you assume that everyone wants to win or get paid. So the numbers are usually positive, and you want the largest number possible. In game theory, in the prisoner's dilemma, the way it was originally phrased, years in prison, you do not want. So you could consider those to be negative numbers. But usually when you look at a payoff matrix, it's written in terms of positive numbers. We just have to sort of reimagine the situation here is that we want to get as much as we possibly can. So if we both cooperated, we both get a 3. That's great. But I'm looking at the fact that if Seth is cooperating while I defect, I get 8. That's good. $8,000 or 8 whatever. Whereas he gets 1, he gets punished. That's sort of the equivalent of me squealing on him. But he's looking at the same thing. He's choosing between this and this. So if I assume he cooperates with me, I'm comparing 3 to 8, I pick 8. I want more. If I assume that he's defecting, and I cooperate, I'm only going to get 1. No way I want that. Whereas I get 2 if I defect. So I'm going to defect. So whether he cooperates or defects, I should always defect. The game's symmetric. He's looking at me, he's thinking, well, Andrew might cooperate, Andrew might defect, but he's looking at 3 versus 8, 8. 1 versus 2, 2. He defects. We both defect. We don't know what the other one's going to do. Not communicating. We both defect. We end up with 2 and 2, whereas if we had only cooperate, we get 3 and 3. It's a dilemma. Prisoner's dilemma. Okay, because this is a symmetric game, usually it's just represented by, we don't have to show player 1 and player 2, we can just represent one of them. And here I'm just saying that it's very general. It's any numbers that satisfy this inequality would be a prisoner's dilemma. Okay, and now this slide, I just want to say that, well, prisoner's dilemma is just one of many games you can have. You choose different elements in the matrix, you get different games. So here's prisoner's dilemma. You might recognize that face. It's an old TV show called Prisoner. There's a game called the coordination game where we both want to play A or we both want to play B. We both want to cooperate or we both want to defect. There's 2 solutions to that game. It's called the coordination game. Birds of a feather flock together. That's why I put that picture. And then there's rock, paper, scissors. Right? Rock, paper, scissors. It's a tie if you play the same rock, paper, scissors. And then the +1 and the -1 represent the fact that that you can win or lose depending on what is it. Rock smashes the scissors, scissors cuts paper, paper wraps rock, however you want to say it. I understand in other cultures there's other objects. Rochambeau, I guess, I think that China is rock, paper, something. It's interesting, the history of rock, paper, scissors. Okay. Now, before I go on, I want to come back to rock, paper, scissors. I just want to say one thing about John Nash. So this is a picture from when he was a graduate student. During his PhD thesis, and Tucker, the same one of Prisoner's Dilemma, was his advisor, he identified a new kind of best strategy. Extremely creative. Actually, he did 2 really creative things. One of them is he came up with this idea of what's called the Nash Equilibrium. It's the best response to a best response. It's not the same as me sitting here saying, what should I do? I don't know what Seth's going to do, so I have to think about every possibility. The Nash Equilibrium is slightly different. You say, everyone starts playing something, and then you ask, is there any reason to move away from that? It's a small difference, but it's extremely convenient. And we won't go into the mathematics of that. But he defined that, and then he had a theorem which he proved to say that every symmetric game, it can have m strategies, m is just some integer, has one of these equilibrium, what we now call Nash equilibrium. And the statement about it is no player can improve their expected payoff by changing their strategy away from the Nash equilibrium. It doesn't say how many there are, but the theorem says there's at least one for every game. Okay, now let's go back to rock, paper, scissors. What's interesting about rock, paper, scissors is it's pretty clear that it's a cyclic game, right? Paper beats rock, right? It wraps it. Rock beats, smashes the scissors cuts the paper. Where's the Nash equilibrium? There is no strategy that no one wants to change from. So let's say we're playing rock, rock. Well, if I know Seth is playing rock and I'm playing rock, I'm just going to play paper. There's definitely a reason to change from that. Right? So you can go all the way around the circle and find that there doesn't seem to be a Nash equilibrium, but 1951 Nash equilibrium theorem. What's going on? Okay, well, this is the other creative thing that John Nash did. He said, let's have the strategy choice be a probability distribution. Randomness, sort of, we don't know what's going on. Is the top going to pull me over or not? Strategy choice is I'm moving, I don't know what you're going to do. The next thing I'm going to do is move my knight. Okay, you have to move, but that's what I'm going to do next. It's a choice. Nash said, let's imagine that the strategy choice is the probability distribution. I'm going to choose that. Okay, so he came up with this idea of mixed strategy. A mixed strategy is a strategy choice that is not a choice. It's a choice of a probability distribution that then tells you what you're going to choose. And for rock, paper, scissors, the Nash equilibrium is 1/3, 1/3, 1/3. So what I need to do is I need to take a ping pong ball and put rock on it, R. Take another ping pong ball and I put an S on it, scissors. Help me not to forget the third one, paper, right? Paper, that's 3. What's the probability that I pull rock? It's a 1/3. So the way I choose, the strategy choice I just made, it's the probability distribution. Now, I'm going to play my mixed strategy distribution against Seth. You ready to play?
Okay.
Hold on. Okay, stay right there. I'm ready. Hold on. I have to talk to the audience for a second. Stand there. Okay. He's getting ready to play. This is what I do privately. I choose from my probability distribution. Rock. Now, I have to play rock. He doesn't know that. I have to play rock. Because I chose the probability distribution, whatever I pull out. Okay, ready? I'm ready to play. Okay, rock, paper, scissors, shoot. Oh, you lost. Lost! Okay, so the probability distribution is, that was not rational. The probability distribution is the choice that I make, and then once I choose it, then I have to abide by it, because that's how the mixed strategy works. Okay, so I just want to make one more connection, so I'm running a little bit out of time. Speaking of Seth, how much time do I have?
Perhaps 15 minutes.
15 minutes, excellent. Okay, I want to take a just small detour into biology now that we've talked about the Nash equilibrium. Okay, it's sort of cool. Mixed strategy means a player chooses each of the strategies with some probability. Here it all is. And then, of course, they have to sum to 1, because I'm either playing rock, or I'm playing paper, or I'm playing scissors. We can't do rock, paper, scissors, and then, I don't know what, I pull out my wallet or something. I have to play one of the 3 strategies. Right? They have to sum to 1. And so we can make a vector out of those however many strategies there are, 3 for rock, paper, scissors, and they sum to 1. But the interesting connection to biology is if you have an organism that's doing a bunch of different things, and let's say you have n of them, you could just take this probability vector and multiply it by capital N, say 1,000. Then I could have 333 of them doing one thing, 333 of them doing another thing, and I can sort of think of the species as playing the different strategies of the mixed equilibrium, the mixed strategy equilibrium, just by sort of connecting this. So instead of having it equal 1, I sort of loosen this up and say the 1 metric, of this m tuple, the length of this thing is just going to be n, and I multiply by n. So each proportion, it's frequency. Okay? If you're a biologist, it's frequency. Okay, so now, what's interesting is, let's take our payoff matrix and multiply it. Okay, it's getting a little mathy now. Let's take our payoff matrix and multiply it by that vector. So I'm doing 2 by 2. It's m equals 2. It's a 2 tuple. So this is just some linear algebra for you. So look at this. It's the payoff for playing strategy 1 against strategy 1 times the probability of doing that. This is just a weighted average. And this one down here for strategy 2, it's just a weighted average. So this is sort of the expected value for playing these 2 strategies as a vector. And that's important. What's also interesting is, if I were to play against someone who's playing mixed strategy U1, U2, this is my expected value if I play strategy 1. This is my expected value if I play strategy 2. The payoff that I get doesn't just depend on the payoff matrix. It depends on the probabilities you have for your strategy choice. Or in terms of biology, the payoff of being a certain species or taking a certain strategy depends on how many of those other strategies are out there. Right? So I want to go, where the let's see, I like oysters. I want to go where the oysters have decided to float on the surface and wait to be picked. Whatever you do with oysters, capture them, scoop them up. Obviously, I don't catch my oysters. I don't even know how to open them. Strategy where the oysters are well glued to the bottom. I don't want to go there because I can't win against that. So I go to the place, the more where there are lots of oysters floating on the surface. I don't actually think that's a good sign for oysters to be floating. Don't eat them. Okay, so the point is that the average or expected payoff depends not only on the payoff, but how many other people you can win against, or the probability that you play that one strategy. Okay, so that becomes interesting when we start talking about evolutionary game theory. And then here again with biology, we're interested in evolution. Some of the oysters are floating on the surface. Well, those oysters, that gene is gone. Not a good idea. Either the birds eat them or we would eat them. Right, so I'm talking about this guy again, playing the game, but now he's playing it over and over again. So now we're a little bit more free. We don't have to think about what's the optimal thing to do. We could just evolve towards it. So evolutionary game theory was an add-on to game theory that was really a beautiful thing. Introducing time freed up our ability to, not only do we have to not find the Nash Equilibrium, we can just start anywhere and see what happens. Right? But we need a rule. We need an equation to specify what's going to happen. And so, we just jumped to that. Oh, I just wanted to say on the way that an important historical point was John Maynard Smith. They had their 1973 paper called The Logic of Animal Conflict. And there's a whole analysis of, why do, I guess these are caribou, competing for mates, why don't they just rip each other to shreds with these driving horns? Instead, they do some sort of, it looks almost ceremonial, and then one backs away, and the other one is victorious. It's like a game. And so it was because of this that Maynard Smith started to think, well, maybe game theory should be applied to biology. I also have to mention fitness. I'm running out of time, so I'm just going to skip this wonderful slide on Charles Darwin and just say that there's a connection between game theory and fitness. It's the expected payoff. And the equation that we use, it's getting very mathy. This involves the game, but I'm going to just show you that what that equation really is exponential growth or decay with a birth rate that's proportional to the relative fitness, the fitness above or below the average fitness of the species. So there's a way to connect sort of fitness dynamics in biology to evolutionary game theory. I apologize that I have to sort of give that very short focus. All right. So the point of this slide is just to say results from classical game theory now get mapped into a new world of these differential equations, and I'll skip the details of that. I do want to tell you that rock, paper, scissors is interesting because you get cycles. And if you do it in space, you get spirals. So this is, Reichenbach has done some things in a distributed group of players playing rock, paper, scissors. This is some work with my PhD student, Russ DeForest, in a partial differential equation, playing rock, paper, scissors, again using that replicator equation with the effective birth rate given by the expected payoff of the game for rock, paper, scissors. These are populations playing rock, paper, scissors against each other. And I'm rushing because I want you to do exactly that. Okay, and I'm going to skip this story of this fantastic lizard, Uta stensenburiana, studied by Barry Sinervo, among other people. There are 3 different male mating strategies for this lizard. And it follows a cyclic rock, paper, scissors like relation. This one, the orange one does better than the yellow one does better than the blue one, I think it's that one, and the blue one does better than the orange one. Okay? So if you look at Barry Sinervo, or you look at these side blotched lizards, you will find that indeed they have mating strategies that are inherited. That's an important point. They're inherited by their kin, by their offspring, that follow this sort of cyclic rock, paper, scissors like that. Okay. Now, what happens if we control the transitions between rock, paper, and scissors? And I need 4 volunteers from the audience. 4 people. And my card guys, wherever the Scion students are, start passing out the cards. I need 4 people. Come up here. Raising your hand, yes. What happens? All right, I need 3 more. Yes. Okay. Yes. We have 3 male members of the audience. Anyone else? Yes. Okay, thank you. All right. Get that card. You're all getting these cards. Scissors. I'll show you how to play this in a moment. Scissors. Here's number 4. Did you? Okay. I might have to put everything else down. Okay, so you are all getting cards similar to the ones that are up here. What I'd like you to do is hold the card, well, what you're going to see them do is hold the card in front of themselves like this in one orientation. Okay? This is what we're playing. I made this game up for you. Rock, paper, scissors with cards. Exactly. So, you're facing, and I want you to find someone who's got the card. You have the card. So, it's facing towards me. Face it towards me. Okay, she's holding rock towards me. I'm holding rock towards her. It's a tie. So, in the case of a tie, don't do anything. So there's 3 rules. Well, I didn't write the 3rd one. Stay. If you win, keep it. If you lose, flip. If you tie, keep it. Okay, so in this case, but we don't have to, so obviously, she and I can be playing against each other. Nothing's happening. Because we can't flip because we're tied. Right, so I would like you 4 to start playing this game against each other. Right? Start playing. Just choose someone to play against. I'm playing against Seth. Oh, so we tied, right? So now, okay, so let's see what happens with these 4. Okay. Let me interrupt you just for a moment. All right, stand back out. Let me interrupt you just for a moment. Look what happens. Okay, now scramble the cards again. Flip them randomly. Flip them randomly. Okay, now start playing against each other. Now I'm going to join the group here. Okay? Scissors, that smashes. Okay, you guys go. You play against, yeah, you flip. Right? So, these people are not playing against each other. Okay, so everyone starts playing against each other. You just can't say the second. You might not want to. Okay, what happened to the 4 up here? All rocks. How are you doing? Show me. I'm looking at your strategies. Here's a. Yeah. That doesn't mean you win if you get rocked. This is means all turned into. Everyone's turned into the same thing. Okay, so what I did in this game. So where is my crew? What I did in this game. So hold on, card crew. Stay right there. I'm going to need you in a moment because I'm running out of time. So we did 4. There's 4 people up here. We did that one. I didn't do the 6th one, but we already started. Whoops. We already started to do the whole room. All right. So I'm going to ask you to do that a little more. But what's going on is, or what I want to ask is, how did we reach extinction? All rock. Okay. So, all right. So now let's. All right. You guys scramble up again. I just going to do a little demonstration. All right. So ready. All right, so go. I, scissors. Okay, so that's. Okay, so paper beats rock. Okay, so I'm winning, so now paper beats rock. Okay, so I'm tied with paper. Okay, so now. Oh no, I'm still paper. Okay, so that beats me, so now I'm back to scissors. So okay, so. These guys are no longer turning into all rocks. I have the paper scissors card. Where's my team here? Now we're new cards are coming out. Just take us put a few of these out. So, if you all got involved and started, I lost the clicker now. if you all stood up and started playing this game randomly against each other, the entire room would turn into rock. Because there is no trend, there is nothing that beats rock, and slowly over time, showing you the equations here, we wrote some equations. So this is work done with Matt Young, he's my PhD student. As I said, I created this card game just to do in a lecture like this, actually for the code. Where is it? Co-lecture game. Okay, so we have variables for the probability or the number of people playing the paper rock card, the number of people playing the scissors rock card, and these are the equations, the evolution equations for those two concentrations. They have two fixed points. Extinction, that means everybody's playing rock. That's what we keep finding. There's another coexistence, but it's very unstable. Okay? But if we introduce, so this is a simulation, and if you run the simulation long enough, so this is, won't go into the details of the numerics, but this is one of the variables x, paper rock, another one, it's the probability of paper, the probability of paper scissors. When it hits 0, everyone's playing rock. So in a certain amount of time, all other species go extinct because it's not directly dominant, but eventually everyone finds, oh, you can go sit down. Okay, nice. So at a certain moment, everyone has sort of found this path, similar to what the equations find, to everyone playing rock. But all it takes is one particular card, this one, paper scissors card, which I have much less of here. The paper scissors card, and then what was happening up here with the 4 is when they were almost all rock, if I was showing scissors and they were all rock, they would beat me, right? So I would flip to paper. Paper beats rock. So now you sort of go towards the more diverse situation where not everyone's playing rock because I have a path to get to something that beats rock. But only this card has that path because this is not really the way you play rock, paper, scissors. But in this game, you flip between two different phenotype choices. So we call it phenotype flips. It's just a card game that I invented as a demonstration. So games, probability. What's next? What's next is I'm out of time. Right? I just want to mention two different things. There's my interest in cancer still there. And I just want to point out something suboptimal about cancer, which you've probably noticed. It's not a virus that makes you sick and then you cough and I'm in the plane and people are coughing and now I'm sick. The virus is doing great. Okay? The tumor gets bigger and bigger. Whatever it does, kills the patient. You know what happens after that? Kills the tumor. It's pretty suboptimal, I'd say. It's a strategy. Okay? So, what's next is, which many of us are working on, is to try to develop or evolve such equations, or try to understand how we might use this kind of reasoning to understand some of the things that cancer does. And believe me, I do not pretend that it's going to be that simple. Okay? Cancer, even the word cancer is misleading, right? There's not just one kind of cancer. It would be great if we could stop just calling it cancer. Right? They're so different from each other. The other one I want to mention is social media. Why do we share what we share? Privacy, it depends on your age in the room. If you have an Instagram account or not. How quickly do you get to 100 likes? Either you don't know what I'm talking about, or you know exactly what I'm talking about, right? I have 3 kids, and it's one of the questions. How quickly do you get to 100 likes when you post something on Instagram? I never get to 100 likes. Not because I have like 6 people following me on Instagram. Right? So I can tell you more about this. I've done some studies on that. I think I'm out of time. But the take-home, the thing I really want you to remember from this lecture is this connection. We have 2 different kinds of games we like to play. Strategy and roulette. Random games. Roll the dice. Okay? They're not so different. In fact, randomness actually extends our ability to make strategic decisions. That's what the mixed Nash equilibrium is. Thank you very much.
comment, or we have time for questions. Is there any questions from the audience?
Hey, my name is Nathan Clark. I'm a sophomore here studying mechanical engineering. I also play a lot of poker, and I wanted to ask you how you see poker, in terms of, is it random, is it strategy? Because yes, the cards you do get are random, but there are plus and negative EV plays that you can make. So I just wanted to see if there is a spectrum of like random and strategy, or is it black and white?
So, yeah, that's a great question. There's a particular, so I have two things to say about poker, and the same thing would be true about chess. The number of possible moves in a single poker game is huge, right? So if you want to draw, what am I going to do? Rock, paper, scissors. Okay, I'm choosing 3, you're choosing 3. Now we've got a bunch of people sitting around a table with a bunch of cards. You're going to call, you're going to fold, and you know, what are you going to do? So, first of all, just the analysis of it is difficult and complicated. But there's two approaches you can take to it from a game theory point of view. One is you can analyze every case individually, or there's something else called the Bayesian game, in which you sort of average over the different outcomes. And I'm unaware of a game theory approach to poker that's useful. I think in certain situations, you might be able to say it, just like in certain situations in chess. But I now realize I should have gone back to the first slide and said that as far as I know, neither AlphaGo nor Deep Blue playing against Garry Kasparov, I don't think either one of those were using game theory. Because there are other ways to do it. For a fixed, I mean, for example, for the chess, I know that it just searches every possible move, and they're playing them to the end. And they're playing all, sort of branching it out, playing it all to the end, and then you're just asking, if this move leads to 100,000 moves, what's the probability that I win in that? And I compare that to the next one. So I would imagine that for poker it'd be something similar.
Gotcha.
So I guess the answer is yes, there are different ways to deal with strategy / probability games.
Are there any other questions from the audience? Oh. Okay, if there are no more questions, then let's thank Professor Belmonte again.